Hello everyone, today I'm presenting our evaluation of 4 FPGA-accelerated space use cases based on neural network algorithms for onboard inference. This work was supported by the ASAP project from the European Commission, and it's a joint effort from hardware engineers and astrophysics scientists. Data in space is increasing. It's increasing because the number of satellites in space is increasing, and also the sensors on board those spacecrafts are generating more and more data. Neural networks can be used to filter this data or compress it. However, those algorithms cannot run on commercial off-the-shelf devices such as your laptop CPUs or GPUs. For that, FPGA-based neural network accelerators are used. They can tackle 3 key aspects. They can tackle radiation tolerance, power efficiency, and performance. Artificial intelligence in space is used for 2 applications, in situ and remote sensing. In situ applications are those that use data that is acquired on the spacecraft. And remote sensing applications are those that use data that is acquired from far away from the spacecraft, such as images of the Earth or images of the Sun. Neural network algorithms are comprised of a set of layers, and each layer is comprised of neurons. Given that set of layers, their parameters can be trained, and then we can infer an input and obtain an output that makes sense. The most common type of neural networks in space is convolution neural networks, which are used for classification tasks. FPGAs are the most fine-grained type of configurable hardware. By configuring their lookup tables and their interconnects, we can execute basically any Boolean logic. In this work, we used the ZCU-104 to prototype our architectures. FPGA-based neural network accelerators can basically follow 2 topologies. Either a data flow topology, where each layer has its own hardware and the data moves from one layer to another, or a time multiplex topology, where the layers on the neural network reuse the same hardware. In this work, we use 2 tools, VTIS-AI and the AMD DPU, and VTIS-HLS. By pairing VTIS-AI with the AMD DPU, we start by converting our PyTorch model into instructions which the DPU understands. Then we load these instructions into the DPU, which was preloaded into the FPGA. However, this approach has limitations. The AMD DPU mostly focuses on convolution neural networks, so it has limited support for other neural network architectures. And furthermore, VTIS-AI quantizes the model into 8-bit integers. And by doing so, and if you do it with post-training quantization like we did, there's going to be a big degradation in the accuracy. Using VTIS-HLS, we convert our ONNX representation of the neural networks into RTL directly. So we get a specialized neural network accelerator. The integration into ZCU board can be seen here in this image. We have our accelerator connected with the CPU. So however, to obtain good performance using VTIS-HLS, it requires manual optimization, and a lot of time can be consumed here. But there's an advantage of VTIS-HLS, which is it keeps 32-bit floating point precision. So the result that we obtain after inferencing the hardware is exactly the same as in software. We optimized 4 use cases. The first use case was the variation autoencoder, and we accelerated only the encoder part on the FPGA. This allowed us to compress the data from an RGB image, so 3 × 128 × 256, to a 6 value scalar vector. And we can see that here on the output we have a 12 value scalar vector. That's because on the FPGA we are executing only the encoder part, and then right on the CPU we are executing the reparameterization trick, which includes an exponential, which should be costly on the FPGA. The second neural network that we optimized was the CNET plus scalar. And these two neural networks are 2D convolution, implement 2D convolution layers. And but we had to adapt them to implement them on the hardware. For example, in the CNET plus scalar, we had to replace the leaky ReLU layers for ReLU layers, because the leaky ReLU layers were not supported by VT's-AI. These two use cases, the variation autoencoder and the CNET plus scalar, were optimized using VT's-AI and the AMD DPU. The third use case was optimized using VT's HLS, because the sigmoid and the greater than function were not supported by VT's-AI. In the original algorithm, it implemented one perceptron at a time, so it had 6 perceptrons with different weights in series. In our implementation, we implemented those 6 perceptrons in parallel. The MMS neural network use cases actually implement 3 different neural networks. Each neural network has a different number of parameters and complexity. However, what's interesting about these neural networks is that they operate on 3-dimensional input data. So the first neural network starts with a 3D pooling layer and then a fully connected layer, while the other 2 neural networks start with 3D convolutional layers. Regarding results, we obtained a very good speedup using VT's-AI for the variation autoencoder-encoder and the CNET plus scalar. However, using the VT's-AI and the AMD DPU increase the power consumption when compared to the CPU-only implementation. Nevertheless, the energy per inference is still reduced more than 10 times when executing with the AMD DPU. By using VT's HLS, we reduced the power consumption when compared to the CPU-only implementation. However, we only obtained a speedup for the smaller neural network models. Therefore, we only got a better energy per inference for smaller neural network models. When comparing with other work in the literature that implements space use case applications into FPGAs, it was hard because not everyone reports the same metrics. However, if we look at our number of parameters and FPS per watt, we can see that our work is comparable to the other in the literature. So in conclusion, with VT's-AI we could obtain a very good speedup for the variation encoder and for the CNET plus scalar. However, this tool has limited layer compatibility and therefore did not support SPERT or the MMS neural networks. With VT's HLS, it supported multiple layers, it supported many layers. However, we only obtained a speedup for the smaller neural networks. One advantage was that it kept the arithmetic fidelity. But there's still more potential to look at in VT's HLS. There's more parallelism to be explored. In this work, we showed that the energy per inference can be reduced using both these tools. Using the variation autoencoder-encoder, we can compress the data more than 16,000 times. The CNET plus scalar, SPERT and MMS neural networks enable selective downlink, which improves the downlink and the data that we have to download. So in summary, FPGA-accelerated neural networks inference is efficient. These are our references, and the last reference is the repository where you can find the code and other experiments. You can also scan this QR code and it will lead you to the same place. Thank you for listening. If you have any questions, please don't hesitate to send me an email. Thank you.